and then you can calculate, 3 different type of recombination, band to band, that basically radiative. You have photon emission, luminescence or fluorescence come out from the recombination. The second one is auger. Auger basically, if one electron or two hole system, that's one electron recombine with the hole from the one electron from the conductor band will recombine with the hole from the valence band. We'll kick another hole even lower. Okay, that's the one electron two hole system. And now you can also have one hole two electron system. That means one hole two electron. That means one electron goes down and then recombine with the hole, and then meanwhile there's another electron was kicked even higher to the conductor band. Okay, and that's why it's NP square or Pn square. Okay. Now we also talk about the triple system, right? SRH recombination. There's also equations there. Okay, you guys can read the slides. We still have a few, tutoring sessions there. Not tomorrow, right? And then maybe Friday, you can ask questions, or you can still ask questions by through email or other ways. Okay. So today we are going to talk about the, I actually combine 3 lectures together. That doesn't mean I'm going to finish the entire slide today. We have 3 lectures. We're going to finish about like 20 or 30 slides each lectures. So total we'll be able to discuss the defect in PV materials, the junctions, and also homojunctions. Okay, we basically will use silicon as example, show what is homojunction look like. Okay, with that, let's get this lecture started. So at the beginning, I have a few slides here, a few video here to show you how to make a chip, and then also how a solar power plant works. And I'm not sure. Let's see if I can play this video. Okay, just a second. See if I cannot. Maybe the link doesn't work. Then that's okay. You guys can find out from the YouTube, find similar videos. Okay. Now let's since we don't have a lot of time, maybe it's good to not to play the videos. Okay. You can find similar videos on the YouTube if you like. So what is homojunction? The homojunction basically, is junction made of the materials which has the same electrical band gap. Okay, the same electrical band gap. Very simple example, what? You have N-type silicon, N-type silicon, you have P-type silicon, then type silicon. Okay, when you form the PN junctions, if this is P, this N, you see since both of these silicon, so their band gap is the same, right? If you dope it, it's tuned a little bit, but they are still similar or the same. So that's why when you form junction, the band gap is the same. Okay, that's called homojunctions. Okay, homojunction. Okay. And then when we talk about homojunction, we basically you see if you have the same band gap for P and N, you form the PN junction from use the same band gap. That's called homojunction. And then now let's take a look at this band gap for many different materials. You can think about silicon is here, right? Silicon, right? And then germanium, aluminum phosphate, and then you have gallium phosphate, and then you have many others. You see the band gap is very different, right? So if you use silicon to make PN junction, you call that homojunction. If you use silicon and germanium make junction, like a silicon germanium junction, and then they call heterojunctions. Okay, and then any of the other materials, if you use 2 of them to make junctions, since their band gap are different, all these are called heterojunctions. Okay. So here for this chapter we'll focus a lot on homojunctions. So now let's see, how does a homojunction work, right? Think about that. Homojunction basically, if you look at these band structures, I can explain a little bit, what is the band structure look like. Just think about, for silicon, since it's semiconductors, right? So you have what? You have this one called EC, that's the energy level of the conductor band. And then here, the bottom one called EV, that's the energy level of the valence band, okay? And then in between of them, basically you have 2 of them, right? One is halfway, halfway here, you see this one, it's called EI, okay? I intrinsic, basically if you did not dope your silicons, you see, their energy, right? Chemical energy will be just halfway between halfway between EC and EV, right? And also, if you dope that silicon to what? N-type, you see your Fermi level will be get closer to what? To EC. That's why Fermi level is here. Okay, Fermi level is here. And then uh, that's for N type. Since here is N type, that's why you add EIN, EFN. Okay, that's why you add N there. Show that's the all this C or this Fermi level is on N side. That's why I call EFM. No, the intrinsic energy level is in the mid gap. That's why I call EIN. Okay, that's for N type. For P side, for P type, you see the similar thing. You still have the band gap between the EC and the EV. Now, if you collect these two, they're the same. See, the band gap is the same. Okay, that's why because both of them are silicon, right? The only difference is that the Fermi level on the P side will be get closer to EV, right? And then that's because you have a lot of missing electrons. When you have a lot of missing electrons, your total energy will be lower. When you have more electrons, your total energy is high. That's why EFP, the P side, the Fermi level is close to EV. And then EI still the same, in midway, okay? In midway, okay. Now let's see. Let's see in the real solar cells, if you think about you use this N-type silicon and then the P-type silicon, you build them together for the PN junction, okay? What will be the building potential, or what is the maximum open circuit voltage you may get, okay? That basically is it's between the EFN and the EFP, okay? The difference here, you see this difference, right? This difference here, that tell you the how much building potential. That's typically the same as maximum open circuit voltage you will get. That's what EFN minus EFP. Okay, EFN minus EFP. And then since the E is energy, right? So that's why it's QVBI, or you can also see QVOC equal to QVBI. Now, if that is maximum, but sometimes you don't get the maximum as that. So we have to see the QVBI equal to EFM minus EFP, okay? And then you see EFM and then EFP. In between them, there's EIN, right? That's why you can see you have EFM minus EIN plus EIP minus EFP. EIP, EFP, if you look at this, they should be the same because both of the halfway, right? See, they're the same level, they have the same values there, okay? And then with this, this one, we calculated that before, right? It's from the equation we discussed before. EFN minus EI, that's equal to what? KT, and then log ND over NI, right? And then the same thing, EFI minus EFP, that's equal to KT multiply log NA over NI, okay? With that, you add this together, you take KT out, that's log this plus that, that's basically, they multiply each other, right? That's why ND over NI square, you can get your maximum VBI is here, okay? It's here, okay? So this is very basic. So if you have N-type silicon, P-type silicon, you put them together, you know how much maximum open circuit voltage you can get. You can also know, the maximum building potential, building voltage inside the junction. So with that, you can see next question probably, if you have this, N-type, P-type, the question to you will be, how do you plot the junction? How do you plot the junction? For that, I'm going to, start a new slide, show you how you plot the junction, okay? So whenever you form the PN junction, you have this, you have force, you have what? You have this. Let's see, this is let's make sure I want to follow the same thing, okay? This is P, right? See, this is P side, type. And the same one is N-type, since this home junction, right? N-type, the band gap is the same. Okay, I call this EC, EC, EV, this C, EV, right? That's EC, EV, okay? EC, EV, okay. And then, since the P side, the Fermi level is what? It's here, right? It's close to EV, right? E, F, P, okay? And the N side, the Fermi level is close to what? To EC, right? We call that EFN, okay, EFN. Of course, in between them, halfway, you have what? You have EI, but here we don't care about EI that much, okay? Now you see, on P side, you have a lot of hole, positive charge. On N side, you have a lot of electron, negative charge. Now, when you put them together for the junction, there'll be redistribution of the extra electron, extra hole, right? They will go each other. Go meet each other. There will be, since P side you have less electrons, the electron try to come from the right side, from the N side to P side. And then since the N side have less holes, the hole will try to come from P to M. With that, eventually, these two energy levels, this one, you know, will be the same. Okay, will be the same. Oh, now let's see. So eventually, these two, N side, P side, we should have the same Fermi level. Okay. Now let's assume I keep one side, fixed, right? If I keep the right side fixed, I keep the N side fixed. If I see here, I plot the N side fixed, here, right? I have this EFN. Okay, that's probably I should plot similar as this, right? That's much. I have this, right? EFN, right? And then EC, EV, okay? And then since the left side, the P side will be aligned with the N side, this N type, and P type. And then the Fermi level will be the same. I need to collect the Fermi level together, this, right? And then, since this how much, from here to there, how much EC and EFP, that distance, I will move the same distance here. You see here, okay, the same distance. And then the same distance here, especially you look far away from the junction, and then this is here, right? Okay. And then now what you see there is what? You see here is EC, then EF, E, right? This EV, right? And then you collect this together. See here, collect this together, collect this together. What do you see here is what? You see your junction, right? This junction, on left side is something like this. Right side is something like this. Okay, this is junction. So inside the junction, you see there's band bending, right? The EC will be bended down, right? From the P side to N side. The EV is also bent down from N side to P side. But now the good thing is that EFP, EFN are aligned, okay? Are aligned. So now if you look at that, how much band bending you have, from here to here. If you look at that, that exactly equal to what? EFP or EFM minus EFP. Okay, that's the distance. See here, here. This is a. I'm going to know this so that not be confused what I'm talking about. Okay, that's a EFM minus EFP, right? EFM minus EFP. Okay, I2. That's so it's clear for you. Okay. Okay, that's here. This is called, V barriers, or you can call VBI, building potential, okay? VBI, okay? So this is how you plot the junction, okay? Do you guys have any questions here? Okay. If not, we can, move to next slide. Next slide, I already plot this. You see, that I just show you, right? Basically, the EF will be aligned with each other, and then EC will be moved up. Whatever is how much is above the EF should stay there. EV will be how much, below the EF should stay there. At the junction, you need to collect them together, okay? And then if you look at the junction here, as I just mentioned, you have built potential. You also have what? Electric field built inside the devices, built inside the junction, right? Now, if I ask you, why the electric field, building electric field have a direction from, this is what? This is a N, right? This N, this is P. Why is from N to P, right? So it's actually, if you ask these questions, that can help you to understand this. Why is that? Because on N side, you have a lot of what? Free electrons, right? When the free electrons from N side, this N side, okay, this one is, maybe I should, put this closer. Okay, I'm gonna put this closer. We can see here. This is my N, right? This is my P. Okay. My N, I probably use the same color, right? I should use the same color here. Okay, this is my N. Okay, and I'm going to use blue. Okay, blue. P is red. Okay, so blue is the N side. The N side, I have a lot of electrons, right? P side, I have a lot of what? I have a lot of hole, right? I have a lot of hole there. Okay, that hole. P side, I have a lot of hole. Okay, so I have electron hole. Since both of the free, one is mobile, both of the free electrons, free hole, they recombine, they kill themselves, right? They recombine, all of them will be gone. And then what you see here, what remaining? Since the free electrons are gone, free holes are gone, you know, when you lost the free hole, you lost the positive charge. So on the left side, what is left is what? The fixed what? Negative ions, right? The fixed negative ion. On the right side, what is remaining there is fixed what? Positive ions, right? Right? Because you lost negative charge, mobile charge from the right side. What's remaining there will be basically what? Positive ions. That's fixed positive ions. On the left side, because it lost the positive mobile charge, what is remaining there is ion. It's not easy if you lost the ion because you have to kick the ions away, right? A electron you can easily, a hole you can lose them easily. So now since the right side is all positive ions, left side is all negative ions, the electric field is from positive to negative, right? That's why electric field from the right side to left side, okay? That's what it means, okay? And then you can see here on the right side, the electric potential is high on the left, on the right side is high, on the left side is lower, okay? That's what you see there, okay? Because it's positive on the right side, negative on the left side, okay? So with that, the electric field from the N to P, and also if you try to plot this, electric field, I'm sorry, the electric potential also, decrease from the right side to left side. Okay, that's how you plot the junction, how you understand the junction. Okay, there are more things here. Basically, if you want to know the charge carrier concentrations on the P side or N side, this one is the P side, right? This is the N side. And then you can see on the N side, because the fixed number of these ions, that's how much what? QND. Why is ND? Because you lost all the electrons. These electrons what? Or these electrons are deleted from the dollar. Dollar is a phosphorus, right? Dollar phosphorus. So how much electrons you lost, that basically how many positive ions you left in this N side. The same thing will be on the left side, will be on the P side, how much positive charge left, that'll be how much, negative ions stay in that side. Okay, that's why if you consider this, the concentration of this charge on the inside will be positive. That's positive. Okay, this is positive. Okay, and then the charge on the left side is actually negative, right? Negative because what? Because you have only negative ions on the left side, and then on the that's negative side is the p side, and then on the inside, on the right side, you have your positive ions there. Okay, with that you can see typically people will use what? Use a p-n junction. They typically we use pn plus junction. Okay, or n plus p, right? N plus p. That basically the n you have much higher concentration compared to p side. So for example, if you have the n side, that's a dollar, right? N side because of a lot of extra electrons because you have phosphorus there. That's the n type. If that 10 power 19 on the p side, if you have 10 power 16, you know that in order for the charge to recognize each other, to clear each other, and then the total charge will be the same, right? Since 10 power 19 is about 10,000 times higher than the p side, so that means on the n side, n plus side, you do not need higher signals, okay? Because its concentration is 10 times, 10,000 times, higher than the p, the p side. That's why the thickness of n side will be 10,000 times thinner than the p side. Okay, that's because of what? Because if you have this charge here, you see the charge, this charge concentration positive, this charge concentration negative, right? The charge concentration multiplies the thickness, right? The thickness, how far it is, because their cross section is the same, right? Because the same wafer, you have same cross section. That's why you just multiply the thickness of the, of the inside in there, and then that should be equal to QNA times the thickness on the P side. Okay, that's why you get this. Okay, if this thickness of the P side, QNA times XP equal to QND times XN. Okay, Now since ND is 10,000 times higher than the QNA, so that means XP will be what 10 times high thicker than the XN. Okay, that's why this layer typically is nanometers. This layer is micrometers. About 1,000 or 10,000 difference. Okay, that's why. And then typically, if you care about the total junction thickness, for example, total junction thickness is basically the thickness of the depletion region. The depletion region basically from here to here. Okay, that's the depletion region. That depletion region can follow these equations. Okay, that's equal to here if this side is the P, right? XP from here to there. And then here is what? XN, right? XN. And then that XP plus XN equal to this, equal to square root of what's inside there, 2 epsilon. This epsilon is actually epsilon naught multiplies the relative, dielectric constant. So, and then multiply this Vbi minus Va. Va basically is the bias, the external bias. Okay, this external bias you add it. But most of the time you don't need a bias. Sometimes you add forward bias or reverse bias, depends what you want to do. And then divide by Q and then multiply to 1 over Na plus 1 over Nd. Okay, that's how you calculate the total junction thickness. So this one is important, right? Why? Because when you increase the concentration, for example, if you increase Na or Nd, now you see what? The total, depletion region get very thin, right? When the depletion region gets very thin, it's very easy for electrical charge to take the tunneling, right? Take the tunneling, okay? That's something we'll talk about later, okay? With that, now you can see, we already talked about the building potential. The building potential basically what? Basically, if you look at this, it's pretty complicated, okay? But what you need to see will be just, if you see this is, okay, let me see where should I start. Okay. Okay. If you see this one is that's not EI, right? That should be, let's see, that should be EFO. It should be EFO. EI will be in the between. EI will be halfway. EI halfway. Get that? This guy from here, if you look at from here to there, from here, here to there, that would be EFM minus EI. Okay, and then from here to here will be EI minus. Okay, this this would be EFP. Okay, EFP, this one minus EI. Okay, and then here, this is EI. This one is EI. Okay, EI minus what? Okay, this will be EI minus EFN. Okay, this is doesn't look right here. I should go back a little bit. Okay. Hey, let me get rid of something here that is more clear. Just a second. Since I added, So basically, okay, maybe this is because this side, okay. This side since what? Since this, if this phi maneuver, see the phi maneuver, this EFP, this EFN, and the only thing is confusing because I think that's EI is right. Okay, why? Because the phi maneuver, this is P side, this N side. Okay, and then on P side, this EFP is close to EV, right? So EI is above that. The only reason it's confusing because this EI is not halfway. The bottom is half. The bottom here is thicker than what? Than the top. That's confusing. Okay, and then so on the P side, you have what? P side, if you look at here, you actually have uh, KT P side, right? P side will have you have NA, right? Acceptor. The N side, you have what? You have ND, is dollar, okay? Dollar. So the P side, if you look at from here to there, that's something I just drew earlier. EI minus EF, EI minus what? EI minus EFP, that's here. That's this, right? EI minus FP is here, okay? That's equal to KT NA of NI, okay? And then same thing here on the N side, since you have what? N side, since you have this ND here, and then the N side, that's FN is close to what? EC. That's why EI is below, EFN is above. EFN is above. And then what you get there? EFM minus EI equal to this, okay? Now, if you have this guy plus that guy, you said what? You get EFM minus EFP, and then that's equal to that plus this. You actually get what? You get this, that's VBI, E VBI, right? E VBI, if you don't take the Q here, equal KT times log NAND over NI square, okay? That's how you calculate that. So if you take this E to the right side, you can use Q, right? Q and E is the same thing. And then that's how you get the build potential. This is VBI, something we talked about. Here, just show you how you can calculate that. We probably calculate that early. Okay, so that's it. Okay, next is I have an example here. Okay, the example shows you basically if there's a p-n junction is formed between the n-type silicon, that's dopant concentration 10 power 17, and then p-type silicon is 10 power 16, and then you need to find out this on the n side, that's what is n naught, what is p naught. On the p side, what is p naught, what is n naught. Okay, so basically if you do that calculation, and first thing it asks you to sketch, right? Sketch the eligible band diagram. What you can do would be what? This is p, right? This, and if this n, this, then when you plot them together, this go up, and then this is there, so this also. Then what you need to do, move the earlier one, right? That's what you get. That, right? This is the LA diagram, and then never or the x-axis. Basically, never what level B, B, what EF, and this EFN here is the EFP, right? EFP, and then EC is C. Okay, that's the first one. You got that, and then if you find on n side, right? This ND on n side, you have what? N9 equal to ND, right? N9 equal to ND equal to what? 10 power 17 per centimeter cubic, and then you get on n side, if you call this N9, right? And then NP9 will be equal to what? Equal to Ni square. This I, this on n side, okay? On the n side, let me get rid of it. And then this Ni square over what? Over this, the bottom will be what? Will be Nd. You see 10 power 20, right? Divided by 10 power 17, you get 10 power 3 per centimeter cubic. And then on the P side, right, you will find the same thing. The P side, you get what? You already know is P, right? P9 is equal to what? PP9 is equal to 10 power 16, right? And then MP9 will be equal to what? 10 power what? 10 power 20 divided by 10 power 16, 10 power 4, right? Now you get MP. And then if you want to calculate the VBI, right? This is the first question, A. Second question, B. And then third question, C. Calculate the building potential, right? Building potential, you can use the equation we just talked about here. Look at these equations, right? These equations, right? You can see that equation. Okay. 2 epsilon R, right? And then the VBI, right? Minus VA, right? And then what is the bottom there? At the bottom, that's Q, and divide 1 over ND plus 1 over NA, okay? And then you take the square root of this, right? That's what you get. It will be what? What you get will be the, oh, that's not the VBI, I'm sorry. So okay, this is a, okay, I'm sorry, I jump over. This one talk about if you use this, what you basically get will be XP plus XM, okay, plus XM. That's what you get is what? The depletion width, okay? The X, okay, equal to that, the depletion width. But what I'm going to show you, this will be the next questions. I think it's okay to talk about here, but I'm going to remove this. So what we need is not this guy. What we need is, VBI, okay? VBI. So how to calculate VBI will be equal to what? VBI is, okay, first I will show you, what is VBI. We just talked about, see the VBI here. I'm going to, this something. This equation for the VBI, okay, for the VBI. That's basically what? C will be what? VBI KT over Q, right? Look at that. KT over Q, right? KT Q, and then log what? NA and D over what? NI is that. The NA is what? NA is 10 power 16, and D is 10 power 17, right? NI squared is 10 power 10, right? That's how you calculate that, okay? With that, you can show you the solution. This is how you calculate that. This is how you calculate the same thing as I just showed you, okay? This is plot this like that, and then calculate, the minority on N side, minority of Q side, P side, and then use this equation to find what? Find the VBI, okay? The second example is actually also about the question I just showed you, You see the depletion region, how width is that? That equal to the equation I'm just showing. I will not talk about that again, okay? This one, right? This is what it is, right? What I can do, what I can do is first to find what? First to find has no bias, and then you find with bias negative, okay? That's basically, and I'm going to show you that, what's the question first about? First, you calculate the VBI, okay? We did the VBI before, we're not going to do this again. That's VBI, okay? And the second question about the width, total width of the depletion regions, okay? That's equal to W equal to XP plus XM, okay, plus XM. Then that's equal to there, right? Then what you need to do to basically find epsilon, right? And then find VBI and also find VA. VA is either 0 or -8. Okay, now let's first see VA is 0, right? If VA is 0, this is 0, right? That's why this is 0, right? Then that's 0. That's why here's 0. And then you plug ND, you plug what? This epsilon, non-epsilon what? R, right? Because you can find that for silicon, right? That's about 11.7. Then permittivity is in the free space about 8.85 times 10 power minus 10 farad over meter. And then you can calculate this about 6.691 micrometers. Now, if you add the reverse bias, now you see that, that depletion region gets thicker because you reverse it, okay? The only thing, everything else the same. Only thing here is what? It's -8. It's minus. That's why because this is minus. That's why this guy goes up, right? The depletion region gets thicker. Okay, so that's about the. Okay, that's about how to calculate the depletion region, the width, also how to calculate, the building potential, and also you should be able to plot the p-n junction band structure by itself, and then you can also calculate, minority carriers or majority carriers in each of these p side or n side. Okay, so next thing what we will discuss will be the contact, right? Because contact is very important. Whenever you make your solar cells, you have either the contact collect electrons or you have contact collect the holes. Okay, okay, now let's see. Our solar cells is p-n junction, right? Now let's see this is what. If you see this one is N, right? This is P. That's called p-n junction, right? Because N is EF. Right? EFN is closer to. Okay, I'm sorry. This is a P. Okay, wrong way. Okay. Because what? Because on the P side, the female is close to what? The valence band, right? Inside the female is close to what? To the conduction band. Okay, that's how you identify P and N. And then when you form these junctions, right, you put contact there, right? You typically, if this hole here, you have a lot of holes, or the hole like the what? Like the flow up. That's you want your metal contact is above that one, above that valence band on the P side. On the other side, since they have a lot of electron here, a lot of electron here, this electron, like rocks, they try to sink, right? Try to sink. You want the metal contact below that, but most of the time you don't be able. It's not easy for you to find the metal that has the work function or that that work function just below the conduction band or just above the valence band. That's very tough, right? Think about this. Let's think about the silicon. Okay, silicon has the electron affinity about 4.05. That's basically what? Basically from here, there, that's the 4.05 over from here, there, that's 4.05. Okay, that's electron affinity, right? And then the band gap is about 1.12 EV, right? That means 4.05 plus 1.12 is 5 what? 5.17. 5.17 EV. See here, it goes here. That's about from here to there. From here to there is what? It's 5.17 EV, okay? 5.17, okay? So that's a 5.17, okay? Now, can you find a metal? No, metal, 5.17 is also here, this one, right? From here to here, from here to here, the same thing, okay, the same thing. Can you find a metal that's exactly, just above 1.17? It's not easy. The same thing, on this side, since you want this contact just below this, that should be just higher. That work function of the metal should be just higher than the electron affinity, 4.05. You can probably find aluminum that's very close, a little. That's good. But sometimes it's not easy for that. Okay, if you go opposite, because electrons like to flow down, roll down, holes like to flow up, right? But if you have this guy, this is contact, if this one is here, if this contact is there, and then you see electron cannot go there, right? The hole cannot come what? Cannot come here, not come here, because the hole like to will flow up, right? So that's why they will form a lot of junctions there. Okay, so that's what I mean here. If you take a look at here, if this is the hole, right? The hole does not like to go down. The hole like to flow like that. If this electron, right, they like to go this way. They don't like to go up. Okay, that's what it means. If you see something go up, yeah. If you see something like this, go up for the electron, go down for the hole, and then see here, there's a diode, right, which has a wrong direction with the main diode in the what? In the solar cell, right? That's photodiode. On the right side, that diode is also of kind of reverse directions with that. And then you have one diode, is major diode, and then you have two other diodes just offset that. That's something not good, right? That's why you don't want something this happen. You want the metal contact here, you want the metal contact here. So this can go this way, this can go that way, or ohmic contact. That's or ohmic contact. Okay. Just discuss something stop myself. And then there's a lot of junction called, PP plus or NN plus, right? We can also form some junction like that. Okay, now let's see what is the PP plus or NN plus. Okay, so basically PP plus, let's see on the P type, right? So the Fermi level is close to what? Close to EV, right? This C, B, C. Also this, and then P is there. Fermi level is just above the EV, but still there's some distance, some separation. But P plus, that, EF is exactly equal to EV. Or can be, below EV, okay? And then this still is C. Now, if you want to form junction between this P plus, what will happen? What will happen there? So basically, the same concept, right? The Fermi never be aligned, right? The Fermi never be aligned. That's basically everything on the right side will push up. Then until the Fermi never is here, right? Fermi never is here, okay? That's what you see here. Everything is pushed up on the right side, P plus, and then the Fermi never is aligned. Okay, this is a new Fermi never. Okay, new Fermi never. Okay, new Fermi never. But at these positions here, on the left side, you see here, that distance still the same, right? Because far away from the junction, that band structure doesn't change. Okay, that band structure doesn't change. See, right? And then, and these positions here on this side, since these two, it's kind of aligned with each other, they're still aligned with each other. Okay, that's on this side, on the P plus side. And then you see you have two plus something like this. This is shift. How much shift do you have here? That's the same shift as what? As this EF, right? EF P plus minus EF E. Okay, that's the separation. And then, if you think about the EI, that also be shift something like this. And then look at the EC also shift something like this. How much shift VBI? That's the VBI. Okay, this will be the Q times VBI. Okay, Q times VBI. And then that's you see here is also p-n junction. See here, actually it's p plus p junction, right? The plus p junction. Okay, so that's the almost the same way you plot this p-n junction. Okay, so now if you want to calculate that, you basically what kt, right? That's the here is kt n plus na plus minus divided by ni. Here will be kt log na divided by ni, and then this guy minus that guy, minus that. Okay, minus that. Put that here. Then what do you see here? This minus this. Then if you plug the n plus, if that 10 power 19, if this na is 10 power 16, you'll be able to see that about 0.18 EV. Okay, see the p plus junction, the building potential can be 0.18 or 0.6. Okay, so with that, you know, uh, here probably shows some learning objective for this combined 3 lectures. Okay, first I would like to review the p-n junctions. Next thing, that's what we just did now. The next thing I'm going to show will be the metal semiconductor junctions. And then the metal semiconductor junctions typically have ohmic contact, or you can also have what? Schottky contact. Okay. But you know that for the solar cells, if you want to reduce the contact loss, you want to get ohmic contact instead of Schottky contact. Okay. And then we'll talk about show you how to plot this band an energy band diagram for PIN junctions, also how to understand the charge densities, also electric field distribution, the potential distribution profile, okay, for the PIN junctions, okay. I think PIN junction is pretty simple. We will focus more on the PIN junction that is more complicated, okay. With that, I think, we talk about this, right? If you know the P side, N side, what is the band structure, what is EC, EV, EFN, EIN, and then on the P side, you have this EC, EV, PIP, EIP, EFP. And then you should be able to plot something like this by yourself, okay? And then you should also be able to understand, how to calculate VBI. That's basically KT, multiply log NA ND over NI square, okay? This is very basic, okay? And then here, a few severe questions. The first question is about which of the following is a homojunction, right? Homojunction, basically, you have N, you have P, this N, P have the same band gap, right? To make the same band gap, the similar way is what? To use the same materials, right? That's why it's what? P-n junction silicon solar cells, okay? That's what? Homojunction, okay? And it can also, the next thing we're going to talk about is, I think here we still talk about the p-n junction, PIN junction, but there, there may not be homojunction. Right in the p-n junction, if you, talk about the, cadmium telluride or CIGS, it is heterojunctions, right? It's heterojunctions, okay? But silicon is homojunction because in the CD cadmium telluride, and then they use cadmium telluride, and then let's see which one is okay. Is this a cadmium telluride? This is okay. Didn't show. This is probably a p-n junction, okay, or silicon solar cell. And CIGS will be the same thing, okay. All this is belong to thin-film solar cells, okay. We'll talk about that in thin-film solar cells. Then PIN, you have gallium arsenide or amorphous silicon. See here, you have P, from here, PIN. Anything else will be just the top contact or bottom contact. So the next thing I think which is important for you guys is something called metal semiconductor junction. Okay, that's important because not only solar cells, even for LED device and many other optoelectronic device, you have to deposit your top electrode, right? Either from aluminum, gold, silver, anything. Or new contact can be what? Graphene, right? Or carbon nanotube, or this kind of thing can be made as a contact. Okay. So ohmic contact, basically, what does that mean? Ohmic contact is electrical junction between two materials that has a linear, IV curve. It's linear. IV curve, you see VI is something like this. Okay, that's called what? Ohmic contact. Ohmic contact, this means there's very small losses, right? Very small resistance loss, interface loss. Okay? And then the Schottky contact, that's a different. Okay, that typically is more like a junction, more like a junction. Okay, if see something like this, Schottky junction. At beginning, if this I, this V is very hot, before you have, it's basically like junction, like diode, right? Before you add voltage that's strong enough to open the gate, and then the current will be very small, okay? So when a metal is deposited on semiconductor to fabricate solar cells, what contact you prefer? Of course, you prefer what? Ohmic contact, right? That would be the less losses, okay? Less losses. Okay, now let's see how can we determine whether a metal semiconductor contact is ohmic contact or Schottky contact. Okay, now let's take a look at the example. Right, this example, if this metal has work functions here, that's what above the EC or the EF on the semiconductors. Okay, and then when you form the junction, is something like this. This called what? Ohmic contact. If there's electron here, the flow like this, very easy, right? It goes to what? To the from the semiconductor to what? To the metal, right? Now let's see if this guy is goes down, move down to here, below that EF on the semiconductors, then you plot this because this line EF and this matter function, that's matter film level, right? You need to align, right? To align, and then this guy will move to here, right? Move to here, and then the distance will be the same far away from the junction, right? So that's here, right? That's here. But since here this guy is about delta E higher than the phi m, so that means these positions, this position still stay the same position there, right? And then you have something like this, okay? You have some. That's what you see here. At the junction, you have what? You have this like this, okay? If there's electron here, it's very not easy for him to tunnel it through. If this signal is very thick, and then you have to climb through these mountains and then jump back, okay? So that's, it's not like this, right? Just roll down, right? Roll down along them here, so you get to the matter. Now it's not roll down, it's up here battle, right? Up here battle. That makes it difficult. So is that you can see the difference, between the ohmic contact and then the Schottky contact. Typically, ohmic contact, you require the metal has work function above the EC, and then for this Schottky contact, that typically requires the work function of the metal will be below EC or even below EF. Okay, that's it. This one is for what? For electron. For electron. Right, for n-type, this n-type. Everything here is n-type. See here, because EF is close to EC, it's n-type. The whole slide here is n-type. The next slide, if you talk about the, okay, n-type is here. Look, this n-type, okay? And then if you talk about the p-type, you get almost a similar sense, okay? P-type. P-type, what do you see here? You still, this is p-type. You still have this matter as a work function here. And then if that matter have work function, above the EF on the semiconductors, EF, because p-type, the EV is below EF, right? And then if this, if this guy, because this EF, they need to align with each other, right? And meanwhile, the distance between here to here, the distance between here to here doesn't change, okay? That means when I move everything up, this position doesn't change because that separation here the same separation, okay? That's what you see here. You move that up and then you move this up, it's something like this. Then you form a junction like this, you see. This is the metal, right? This is what? This one is semiconductors. If there's electron here, they can flow easily to there, just roll down, right? Roll down from the, top of the here to what? To the metal. That's called what? Oh. Okay, this is that, but unfortunately here we talk about the p-type. So this is not electron because this what? This is a Vb, right? Vb, okay? Vb, okay? Vb, we need to change this to what? Sorry for that. I should write whole instead of electron. That's the whole, right? So the hole is a bubble, right? The bubble doesn't want to go down. Bubble like to go that direction, right? The flow up, right? So that's why in Schottky contact, that's if bubble goes down, that's what Schottky contact. Okay, so your bubble should flow up. Okay, flow up. Okay. Now let's see if this work function of the matter is below the EV. Okay, below the EV. Okay, and then what you see here there is here there because this one will be aligned with this. Aligned with this. And then on this side, on the other side, this should be go the same distance, right? But unfortunately here, this guy is that much taller than this, right? This should be what? That much taller than this, you know. This is a matter. Yeah, okay. This is like that. Everything pushed down, right? Everything pushed down, but oh, that okay, not that tall, right? This is a okay. This is a EV, right? That's EV. That's not that tall. That's the EF. That's EF. Okay. So I should not draw that. That's too tall. Okay. Too tall there. Okay. So it's just this much tall. Look, this much tall. See here? That's much tall. And then that means if the junction is here, it do like that tall. How much tall there should stay there? Okay. That's why I see here. This guy still stays there, right? Above, right? Above that, above this EF. Above that EF, that's still above of that EF, okay? That EF on the metal, right? That's why you have a bubble here, the bubble like to flow up, right? So the bubble like to flow up is, uh, uh, it's kind of, energetically favorable, okay? Energetically favorable. That's why the hole just flow up. That's what you see there, okay? So this is called what? Ohmic contact, okay? So, uh, okay, this see here, if what is the work function, compared to that semiconductors, either Fermi level or conductor band or valence bands, you'll be able to identify, whether it's ohmic contact or Schottky contact. Okay, so that's just you just delete everything here. So you can So the trick is there, at the junction part, this delta E doesn't change. The same thing here, delta E doesn't change. Okay, the same thing here. If you look at here, the delta E doesn't change. The delta E doesn't change. Okay, that's help you to identify, whether it's a ohmic contact or Schottky contact. So okay. Next thing about the tunneling, right? The tunneling basically, if you have the band bending, right? If the band bend is very thin, the electron can just tunnel through, or the hole can also tunnel through, right? Like the wall, you think about the wall of the buildings. When the wall is make what? Make concrete, right? And then very thick, nobody can pass through. But how about the wall made of paper, right? And then anyone can tunnel through, right? You can just, collide with the wall, this vessel paper. You just, tunnel through by yourself, right? The same thing for the electrons. If the band bending, is so thin, especially you have very high concentrations like this, and then the electron hole can tunnel through like this. The hole is here. They don't need to go like this. They can just tunnel through that, okay, to the contact. That's about tunneling, okay. I think it's good, we can stop here because the next thing about how to draw the PIN junctions, we'll probably take the second lectures, discuss this. Not second, the next lectures tomorrow morning, my time, we'll discuss that. And then right now I can take any questions with 5 minutes, just in case. Make sure you guys understand what I'm discussing here.
Thank you, sir. Participants, if you guys have any question, you can raise your hand. So we have one question that he has asked very early, but I guess you have answered in the slide 20. He was asking how to draw band diagram if both semiconductors are N-type.
Okay, so it's a matter semiconductor contact or the p-n junction p-n junction? Which is his question between metal and semiconductor or just between the semiconductor itself and type p-type?
Hello, Mr. Kishan, you can ask your question.
Yes, sir. I was asking like NN type semiconductor junction, but I think you have already answered in the next slide. So I
Oh, so
understand.
like N plus, is that NN plus or PP plus? Is that the junction you talk about?
Yes, sir. I understand NN type junction now. You have answered in slides.
Okay, great. Thank you. Thank you. Yeah. So I have to suggest the students can draw the, uh, metal semiconductor junctions because this one can be very, tricky here. Okay. I would, you see the slides here. You can plot it by yourself. Okay, by yourself. Okay. When you plot it by yourself, you understand how to plot it. Okay. So when you
Hello.
plot any junctions, yeah, go ahead. Yeah.
Yeah. Yeah. Yeah. My question is that if this the for the N-type semiconductor, if we trying to make the Schottky, sorry,
Yeah.
for the ohmic contacts, so if the work function of the metal is low, okay. If the work
Yeah.
function of the metal is low, so there will be some band discontinuity between the conduction band and the Fermi level of the metal. So, like in this case that it is mentioned in the figure.
Yeah.
So,
You're
if
talking
this,
about, yeah, go ahead.
yes, if this will be high, then is there any negative impact on the contact performance?
So which you're talking about this one or this one?
No, no, left one, left one.
Or the left one, okay?
Yes, yes.
Left one. Okay, that's a great question. Thank you. Thank you. Good question. The left one, right? Are you talk about just this part? Maybe just a second, okay? Are you talking about this part? Is that your question? Oh no.
Yes, exactly, exactly, exactly.
Okay, okay, great, great. Now you know what? Because okay, that's a great question. I like the question, okay? Because look at here. This is the matter, right? The matter is a feminine verb, right? But matter, any of this state is what? Is active, right? So if I plot that here, but any state here connected with this is very conductive, state there, conduct band, right? So the doesn't matter my electron has two jumps there, can go anywhere. You know my point?
Yes,
Because
yes,
the matter, right? Matter you state everywhere is you can transport anywhere. The state doesn't make any sense. There's no higher or lower state, right? So that's why, even it's here, doesn't matter, right? Because whenever your electrons get to the metal, it's transported right away, right? You got my point?
yes, yes.
Yeah, that's probably the way to answer. Thank you for the question.
Sir, I have a question about tunneling. So, hello.
Yeah, yeah, yes.
Yes, sir. So you have mentioned that the tunneling will happen when the carrier concentration will be greater than or equal to 10 to the power 19 per centimeter cube. So is that only
Yeah.
condition for this? It this depend on the this band offsets also. Like if there will be high band offset, then tunneling will happen or not?
Oh, yeah. So if you look at this, how much is bending here? This bending depends of this, how much here. That also depends of concentration. The bending not only concentration also depends of the see here VBI, right? And then VA, you know, if you add bias, the bias can also have the bending more, right? Because you kind of push down, right? Push down
Yeah.
and you bend more. So yeah, you're right. There's other factors, but here when I talk about this, just assume the other factors like the bias, the VBI is a similar sense, and then your higher concentration will be able to bending down more, right? Because especially on in plus side, if this is 10 10,000 higher than the P, this layer will be very thin, right? The N plus will be very thin. That's why, the bending will be very high. And then the electron or hole can pass through that N plus layer very quickly.
Okay, sir.
Okay, great. So tomorrow, the plan is that first I'm going to teach one lectures here, how to, plot these PIN junctions, how to calculate, how to calculate the current density, and then the electric field, and then the electric potential inside the junction, okay? And then after that, there'll be a demo, right? Unfortunately, this is online demo, right? We have the cloud box in the lab. There'll be one student, Raja, he's also from India, and then a lot of students, I think Yucheng from China. These two students will show the demo to you guys how to fabricate perovskite solar cells, okay? It will be online. The student will do the experiments. A lot of students will be, just video it. You can see real time, okay, like FaceTime, something like that, okay? So that's for tomorrow's plan. Okay, so if there's no question, we can stop here. I know it's pretty early for you guys, right? You probably have other class to take. Okay. Yeah.
Yes, sir. Yes, sir. Thank you, sir. Thank you so much. Maybe we can
Great,
take
great.
a few questions later in the evening, in the tutorial session. But for now,
Yeah,
we can close the session, sir. Thank you,
okay.
sir.
Great, great.
Thank you, Professor Chow. Thank you.
Yeah, no problem. Thank you, Mahesh. Okay,
Thank you.
Mukesh. Okay, bye bye. Yeah.
Bye.